recording. Okay, so let me actually ask this. How was your lab the other day, on Tuesday?
Tuesday?
Yeah.
It was pretty good. You got into like a rhythm with X-Foil, just doing it over and over again. Mine had some problem for some reason, so I just got a lot of extra practice with it.
Huh.
But it worked out.
The good thing is you can install on your laptops or computers. If you have, I assume all of you have a laptop or computer at your disposal. So you can definitely work with it, work on it yourself. Okay, so the next lab you are going to have next week on Tuesday is the tensile test. And the lecture talks about the tensile test, but before talking about the tensile test and like the theory behind it, we will have an overview of statistics. So the statistical analysis you're going to see today, it shouldn't be anything new to you guys. You all have passed the statistics, right?
Taking it now.
No, not yet?
I passed it. I mean, I've taken it before in high school, like college level statistics, and I'm taking 509 right now.
Okay, so it should be, I mean, there's nothing hard about the statistics we do in this class. We're going to get into a little bit of detail, more detail in the next class, in the lab 2. But the general discussion is going to focus around the mean, median, mode, a standard deviation, a standard error, and then we will move on to the basics of stress and strain. And we'll talk about the deformations a little bit. We will see the stress and strain curve for metals and also for composites. So let me ask you guys this. You have passed your mechanics of solids, right?
Mm-hmm.
Yes? Statics and mechanics of solids. Okay, so you have seen a stress strain curve. Yes? Okay, that's good. Yes. In general, whatever we do in the class is just a review of the theory you have already learned, right? It is alright if you don't remember it or if you don't know it. You just have to let me know that you don't know it, so I can go in a little bit deeper. So let's start with the statistics. A statistical analysis is the science of data collection and data interpretation. We use formal probabilistic methods for drawing inferences and making decisions from these data. Okay, essentially the steps you want to take in a statistical analysis is to summarize data, is to maximize the information derived from your data, is to test an alternative hypothesis or models to see whether they are if you can actually nullify them, if you can say they are not valid, and then compute the probabilities of future occurrences. And afterwards, the final thing you want to do is to make rational decisions based on the data and information. So for most of your lab reports from now on, I expect you to do some sort of a statistical analysis, if it's possible to do so, right? So I expect you to calculate the standard deviations and calculate the error, and so far and so forth, right? But the statistics in general quantifies our ignorance, which means it essentially means that it quantifies the uncertainty of our measurements, right? Statistics are about ways to describe our previous experiences, are useful as guides and motivators, are generally poorly understood and often abused. In the wise words of Homer Simpson, we can say he actually came up with this in one of the episodes, said this in one of the episodes, that people can come up with the statistics to prove anything. 40% of people, for example, know that. So what is wrong with this sentence? Or is this true that people can come up with a statistics to prove anything?
You can kind of phrase however you can phrase what happens in like a couple different ways. So if like a situation like I had say like 5 cars and I got 10 cars, that I have like a 100% increase, or did I
Okay, what's wrong with that though?
Because depending on how you phrase it, it changes people's opinion of it.
Okay. So let's try to talk about a very hot example these days, like the presidential elections poll numbers, right? You always hear, yes.
I was gonna say people can skew the data and not show the error that could be received within the data.
Okay, exactly. So these are all valid concerns that you want to talk about, but to actually talk about this problem, that you can come up with any statistics, and you can come up with statistics that prove your point. Let's talk about the poll numbers, presidential election poll numbers. So it happened in 2016, and it always has happened. It is nothing new that people usually rely on polls so much, and then they don't get the result they want. Why do you think that is? Because that essentially, in essence, is the same thing, right? People use a poll that proves their point, and then eventually they don't get the result they want, right? Right?
Doesn't it also depend if it's like a random group of people or people who would have volunteered to take this poll or something like that?
Okay,
Yeah.
so sampling is very important in statistics. That's what you're saying, right? If the sample you're choosing to do your analysis on is a representative of your population, right? Like if you're dealing with a group of human beings, that a group of voters, right? And you want to get an idea on which way they are going to vote, you have to make sure that your sample represents the population of voters. For example, you have working class people and rich people. You have like out of every minority and majority, right? You have a good representation of everyone who is going to vote, right? So that's one problem. What else is the problem with the representation of presidential polls?
The number of people versus the population you're trying to compare it to, like your sample size versus like the full population.
So what you're saying is the sample size should be large enough, right?
Yeah.
Which is essentially along the same lines, right? And I want to discuss it more. Anything else?
How the polling is conducted, because it could be kind of like a ranked format instead of an either or, and that could change how much percentage they would get.
Or the way the question is phrased too, could
Yeah.
be biased towards like, what would be a reason you would vote for Trump over Hillary? And now it's like induce some people to answer one way versus another.
Yeah, that's right. Yeah, so a lot of Hillary supporters would answer that. Yeah, no, I get. Yeah, you're definitely correct there, and that applies to a lot of surveys. But that doesn't really play into the statistics part of it. Like the statistical analysis will be there that talks about the surveying problems, right? The questions you have. So what other more important? There is one more important part of it that relates to us a little more, right? Like a survey, we don't survey metals, for example, right? Metal, you do an experiment on it. If you're doing the correct experiment, you are good, right? So the metals won't provide any answers based on their feelings, right? It's a metal, it will break or not. That's it. But there is one more thing that is related to our work a little more, as far as massaging the statistics part goes.
Do you mean like outliers?
No. Outliers can always be a part of your analysis. So what actually I want you to get at is the margin of error that you always have to present with your statistics, right? So in presidential poll numbers, they say like in the upcoming presidential election, we have Biden and Trump, right? They say, for example, Biden is usually higher, like 47 to 42, right? But they usually don't mention the margin of error, which is a very important part of your analysis, right? And we will talk about it. I'm pretty sure you have seen this in your previous statistics courses if you have passed any, but we will also talk about it a little more. The margin of error part, what does the margin of error tell you?
There's certainty that the value is going to fall within, that like 10% margin of error, for example, would be that space that data can fall within.
Exactly. Do you guys have anything to add to this? Okay, so essentially, what it means is that the real, to go back to the presidential election part, the real approval rating of like Biden, for example, or Trump, is not 42% or 47%. We don't know that. We only know that it is in this specific range, from like 39 to 49. That's what we know. So my point is, what I want to get at is that when you're dealing with an engineering analysis, or when you want to calculate the standard deviation, or whatever, when you want to make a measurement, you always have to keep in mind that you cannot, there is no way for you to be able to measure a true value of something, right? There's always an error part, right? So you always have to be mindful of that. That's why you repeat your experiments, to be able to give you a range, right? So my true value will fall in this range, but I don't know where that is, right? Of course, you want to narrow the range as much as possible, but it's not it doesn't necessarily always happen. Okay? Is there any questions? No? Okay, so let's move on. And statistics is a specified determinable function of a set of observations. Let's assume we have n measures of some random quantity xi. We can calculate various statistics, such as these very simple examples. We can find the sample size, which is your n. We can find the sample sum. We can find the sample mean or arithmetic average of the sample. And we can find the sample sum of squares, as well as the range of your observation. But there are some important parameters that we can measure, which we refer to one of them, or we didn't talk about the other ones, that need a little more discussion. The first one is the mean. And the mean is the thing that we mostly use in engineering, right? Whenever you're measuring something, whenever you're doing some sort of calculation, and if you have to do a statistical analysis on it, the mean is the value, is the thing that you want to calculate compared to the other two important measurements that we are going to discuss. But the first one is always the first thing we always discuss is the mean. What is mean? Mean, or arithmetic average, is the sum of all of the data divided by the number of the data points, right? The notation you're going to use for the mean depends on whether you are dealing with a population or a sample. So you're going to use mu for population mean, and we're going to use for x bar for a sample mean. Let's say you want to calculate the modulus of elasticity of a specific type of aluminum. Okay. How you want to go about it is essentially to get us like 5-10 dog bone samples. Have you seen a dog bone sample? You know what a dog bone sample is? You will see it in the lab next week. Essentially, a couple of samples of aluminum, test it a little bit, like get the stress strain curve, and then take the linear part out. We will talk about all of this later, and then calculate the modulus of elasticity. Right? That's what you do. Right? So, my question for you here is that let's say you are doing this. You are essentially finding 10 moduli of elasticity, right? And you want to calculate the mean for them. Which of these means are you calculating? Are you calculating the population mean or the sample mean? Sample. Why is that not a population mean?
Because if you're just using a specific bar of aluminum, it's not. It couldn't be representative of every single piece of aluminum ever.
Exactly.
This specific aluminum.
Exactly. So essentially what it tells you is that in most of our analysis in engineering, we are not dealing with population. Yeah, it is not possible to deal with. You cannot go out and measure the modulus of elasticity for every, what was your name? Sorry. Lawson, yeah. As Lawson mentioned, we cannot go out and measure the modulus of elasticity for everything. So we usually deal with the sample mean, and this is how you calculate the sample mean. If you remember, the sigma sign here, the summation sign here, it essentially means that you just add all of the observations and divide it by the sample size. The next operation that we can do, or the next important factor in a statistical analysis, is the median. Median is essentially the value of data point in the center of your data set when arranged in an ascending or descending order. So what does it mean? To give you an example, let's say these are the observations you have. You have 1, 2, 3, 4, 5 observations, right? You just have to order them in an ascending or descending order, right? And you take the third observation, which is your middle observation. It's going to be your median, right? The median here is 325 because it's in the middle. But what would happen if you had an even number of observations, let's number of observations? How would you calculate the median?
You take the two middle values, add them and divide them by 2.
Exactly. So essentially, you take the third and fourth observation after you have already ordered them, right? You just take the average, you take the arithmetic mean, essentially. This is an example. Then the next thing we want to talk about is the mode. Mode is one or more sets of numbers that occur with the greatest frequency. For example, in this data set, number 9 has occurred 3 times in this observation. So the mode of this data set is 9. And since 9 is the only number that has been occurred 3 times, it is a unimodal data set because we have one mode on it. But if you have 2 modes, for example here, your mode is 4 and 7 because 4 and 7 are occur 3 times each. And we call this bimodal. We call this bimodal data set. A data set can also have no modes. It can be a uniform data set. But as I mentioned, you can use mode, median, or mean in the calculations in your statistical analysis, but we mostly use mean in engineering analysis because we are dealing with numbers, right? We are dealing with numbers. Let's just stick to that. And with numbers, mean is the best representative of the tendency of your data. The next part is the next thing we want to discuss is how to make a histogram. What is a histogram? Who can tell me what a histogram is? I'm pretty sure you have seen millions of histograms in your life, right? So this is nothing new to you guys. But what does it represent? What does a histogram represent?
It's just like a bar graph with numerical values.
What does a bar graph represent? Frequency of your...
Of how many times the data points occur.
Okay, so essentially when you want to create a histogram or a bar graph, right? A bar graph is different from a histogram, but they represent the same thing, right? What you want to do is to create bins or ranges for your data, right? Let's say your data goes from, the first thing you want to do is to find a range. Let's say your data goes from 0 to 100 and you want to have 10 bins, right? So you essentially create a bin that goes from 0 to 10, 10 to 20, 20 to 30, and so on and so forth, right? And you check how many data you have that goes into the first bin, right? That will be the frequency of the first bin happening, right? And the frequency of the second bin having, third bin, and fourth, and 5, and 6, and so on and so forth. And then you just present that frequency on a plot. For example, we have the heights of 100 residents in somewhere in Canada, anytime in Canada. We can draw this table. We can tally the bins essentially. The bins, we wanted to have 10 bins, and the range of the data was from 4 feet to 6.5 feet, right? To divide this into 10 bins, we essentially have to go every quarter foot essentially. Every bin's length is a quarter foot, okay? And then you count the numbers the data that fall into each specific beam. You have the frequency. You can draw the frequency on a histogram that looks like this. Okay, as Lawson mentioned, and Igor. Okay, well, what do histograms represent? They are statistical tools, as we said, for showing the frequency distribution of the data. But more importantly, they give us some information about the location, spread, and shape of the data. Right? For example, a couple of important data shapes of the data. We have the most important type of this data distribution, which is a normal distribution. Then we have a skewed right and left distributions, B and C. We have the truncated data distribution, this one. We have a bimodal distribution and a uniform distribution, which is just a uniform distribution. We talked about the distributions. Okay. Let's talk about the outliers. So as one of you brought up outliers, but it was you, right? But we may have, in our observations and measurements, we may have outliers, right? So what are outliers? Outliers are essentially data that are very far away from your other measurements. Let's say you are doing a measurement of height. Most people fall within 4 feet and 7 feet, right? But if you have someone who is 10 feet tall, then that person is an outlier, right? What should we do with that person in our statistical analysis? What should we do with that measurement? We don't know if there's a person behind this measurement or not, right? What should we do with that measurement? That's an extreme value. The first thing you want to ask yourself is always whether this extreme value is a valid measurement or a very huge error. You don't know that at 10 feet, that 10 feet person was just 5 feet and the guy that made an error in the measurement, right? The person who was measuring the height. You don't know that. But it is very highly possible because most people are not 10 feet tall. How many meters is 10 feet? Like 3 meters, right?
2.5, I would say.
No, 3 meters, exactly 3 meters.
Oh.
Each foot is 30 centimeters, right? 10 feet is going to be 300 centimeters. But it doesn't matter. 10 feet is very tall, right? Doesn't really happen. Okay. So what should we do? What should we do? That's the question I have for you guys.
If it was you conducting the experiment, you should probably first determine if there's a chance for an error like that to occur. And then you should find your standard deviation values and determine how the magnitude of how far away 10 feet is from the average. Then determine if that is like a significant amount or tolerable within the bounds of the experiment.
Let's say it is a significant amount. That's the idea, right?
Yeah.
The idea of an outlier is that it is well out of your normal distribution of the observation, right? Can we just remove that outlier and conclude it's an error, or should we do that? How should we deal with outliers? Because the presence of an outlier will change your final statistical analysis, right? It will definitely change your average, that's for sure, right? Let's say you have an observation of 2, 3, 5, 6, and 100, right? Your arithmetic mean will be different, right? With and without the will be very much different, right? With and without the 100 measurement. Can we just remove that, or is there any steps we should take? Yes.
If you're able to, you can do multiple iterations and see if the outlier will still occur.
Okay, that's a very good way to go about it. So, but in general, you have to do what Igor mentioned. You cannot just remove the outlier. It doesn't really matter how much of the statistical analysis you do to determine whether that is an outlier or not. You cannot just remove it, right? You cannot essentially censor the data just out of nowhere, right? And mainly because sometimes these outliers are the thing that you may be looking for. very famous example of the outliers are the Nobel laureates, right? How many Nobel laureates we have in 7 billion people on Earth, right? 50, 100, right? So that those people are the outliers, right? You don't want to just kill those people because they are outliers, right? So you just have to be very mindful of that. When you are making a measurement, you cannot just remove an outlier. You have to make sure you deal with it, of course, but you shouldn't just remove it. Okay? So mainly because, as we said, censoring of good data always introduces bias and always makes the data look better than it really is. So let's say you want to calculate the average IQ of everyone around the world. If you remove the Nobel laureates, your data will look more like a normal distribution, which is it does look better, but it is not real, right? Because we have those people that are out there. And some softwares do automatic censoring, if you will, but we don't really do that. We do most of our statistical analysis by hand in this lab. So not by hand, but I mean you have to do the calculation either in Excel or whatever. Okay. So with this, with the mean, mode, and median all of the way, with their definition of the day, and a small talk we have had about the outliers, we can get to the descriptive statistics. Essentially, we use the statistics in general to describe our data, right? That's the goal in engineering, in our class as well. And the first thing you want to do in a descriptive statistic is to find the central tendency of your data. Right? And what do we use to find the central tendency of the data? Is to find the median, mostly median. Find the mean in our analysis. But in general, mean and median will give you the central tendency. Essentially, they tell you where is the middle. But most tell you the most probable bin range for the data. And then we get to this new definitions of a standard deviation and range, which will give you the width or the spread of your data in general. How wide is the distribution? Okay. Let's talk about this measure of variation or the width of the data a little more. A measure of variation is a number that indicates the extent to which your data are spread out around the mean, right? So the mean is the first thing you calculate, and then you want to calculate the standard deviation. We have standard deviation, variance, we have the range, which essentially tells you how far is a given data point from the mean, or what is the deviation from the mean. So let me ask you this. Let's say we have these two data sets. Okay. Which one has a bigger standard deviation?
The one with more spread.
The flatter one.
The flatter one. It is very obvious. Essentially, if this looks like your mean, this is the central tendency, right? This one is more spread. Very simple, right? And what is the goal here? Do you want to have a higher standard deviation or a lower standard deviation, or you don't really care what is the standard deviation?
I think it depends on what you're measuring in the context of the statistical analysis.
Okay, can you give me an example of the two sides of it?
If you're okay with having a less homogeneous population, you're going for diversity of response, then standard deviation isn't necessarily a bad thing, or like you want a uniform distribution. But if you want, say, like a normal distribution and you want everyone to be around the same value, if you're going for more of like an equity outcome, then you would want a smaller level of standard deviation.
That's an interesting look at it. Okay. Anyone else?
I nodding to agree. Oh no.
Okay. So essentially, what Lawson is telling us is that it depends on your data set and what you're observing, right?
And what you want to happen.
Okay. So essentially,
Like you could use economic systems as an example.
so you want to have some poor people and some rich people. Is that what you're saying?
Yeah, like in a capitalist society, you want to have like a large standard deviation, but like say in a more like communist leaning society, they want everything to be like homogenized, regardless of where that is on the axis. Like,
So let me ask you this then. As you brought up economics, that's a very good example. Do you want to have like a distributed society, or is this something that naturally happens?
I think it's something that naturally happens.
But I don't think the goal is to have poor people.
No.
You want to have everyone.
No,
You
yeah.
want everyone to be as rich as possible, but
Sure.
it doesn't really happen, right?
Yeah.
So your goal is not to have like diverse sets of incomes, right? You want to have the highest income for everyone, but it doesn't happen, right?
Mhm.
So we can get to the fact that from this we can get to the fact that there will always be a standard deviation in your measurements, but it doesn't really necessarily mean that your goal is to have a standard deviation.
I guess like your goal can change the size of the standard deviation, in a sense.
Okay, how would that be? Let's try to find an example, right? When you're measuring one thing, right? And let's try to in measuring one thing for which the standard deviation, having a widespread data set is a good thing.
For the widespread data?
Yeah, a widespread measurement is a good thing, right? You may, huh?
Let's do age. You want a widespread of age.
But age is usually not a measurement, right? If you want to have a representative sample, yeah, you want to have a widespread like range of age, or you want to include all minorities, everything, right? You want to have all, but that's not a measurement, right? That's just a part of your sample size. If you're dealing with population, we don't really do age in engineering, right? You don't care how old your aluminum is.
It's really old.
I assume, yeah.
Structural rust.
I mean, for the small standard deviation, if you're measuring like elongation, if you pull aluminum, you want a very small standard deviation so you can narrow down like what is your mean elongation so you can plug that in to find your stress and strain and all of that stuff.
So, okay, I think there is a small confusion. If I understood what you said correctly, I think there is a very small confusion. So if you are only measuring one elongation in one sample of one aluminum, right? That you cannot calculate any standard deviation
No,
for it.
right, but I mean like in a sample of aluminum, like
Aluminums, yeah. You want to have the same elongation for the same force, right?
yeah, you want
That's it. So you want to have essentially your goal is to have a zero standard deviation, right? Does that make sense?
yeah.
Okay. That's what I wanted to get to. But you brought up some good points, which I'm still struggling to find a good example for it.
I can make one up, but like it's not ethical. Can I go for it?
Yeah.
Okay. So say you have like a ride sharing service amongst like a group of friends, and it kind of like picks a random person out of say like the 5 of you who has to like pay for the Uber for that night. If I didn't want to pay for it that often, or I wanted it to be really equal, I could change how often it would like gravitate towards, like I could change the amount of like the pie chart of like, say it was like me, John, Jeff, whoever. It's like I could change our percentages that we would get it to have like the most equal outcome, or we could have like someone has the biggest because they, I don't know, like they have the highest paying job, and then they just get smaller depending on your income, and then that would change the standard deviation of how many times someone gets it.
Well, that doesn't really talk about any measurements though. It's talking about how good is the deviation of your randomization system. How optimized is your randomization? Does that make sense?
Mm-hmm.
Okay. So for the engineering purposes, for the elongation purposes, let's stick to the 0 standard deviation. Right? We want that's the goal, but it never happens, right? And yes, yeah, and there are, as we have mentioned, as we have seen before, there are 3 ways of indicating with a number how far xi, one specific measurement, is from your is from the population mean. Okay. But how can we calculate this standard deviation? What is the formula for it? Does anyone remember?
Isn't that the square root variance?
The variance is the square root of variance. Yeah, it is. So what is the variance then?
Oh gosh.
It's like a fraction with a whole bunch of stuff on.
Okay, so this is the main equation.
That.
Yeah. This is the main equation for the standard deviation, which is the summation of each observation minus the mean, the arithmetic mean, squared over the number of the observations in your data set, a square root of this, whatever I said. Okay? But the question I have for you is that why aren't we doing just a summation of, why aren't we just getting rid of this 2 power and the square root? Why aren't we just having the sigma xi minus mu over n? I would assume that will give you a better idea of the spread, right?
You're talking about why the square is there?
Why is this? Why is the square root and also the power 2 is there?
Well, you want it to be a positive because you can't take the square root of a negative number. So x minus, what if, u is too big, you'll get a negative number, but if you
So-
square it, it'll be positive.
What we could have just put an absolute there, right? It will give you a positive value. But a spread is just doesn't really matter if it's a negative value or positive. You could have just taken out the positive value.
Does it serve to normalize the data?
Normalize that. How does it normalize that? What do you mean by normalization here?
I suppose, like, try to just trim it up as nice as possible to be sure that what you're getting is the, where am I going with this?
So the square is gonna produce a certain kind of graph. So that's why the absolute value won't work. Because if you want a distribution, squares will give
So
you
let me give you this example. Let's say we are all measurements, right? Right. Let's say we are all in the coordinate system, and I'm the mean, right? I'm going to find the spread from the mean. Is it better to just find this distance between me and Lawson and Igor and Nirdev, right? Or is it better to take it to the power 2? Which one shows the deviation better? The distance from the mean. I assume just subtracting our position, just calculating the distance you guys have from me, will give you a better idea of this spread. Right? Does this make sense?
So the square just exaggerates the distance.
It essentially does, right?
So
So essentially, what we are doing is that we are taking to the power 2, we are exaggerating the distance, then we are dividing it by an n, and then we are taking the square root to remove that exaggeration. But that doesn't really work that well because we have already divided this by an n, right? So it doesn't really remove that exaggeration. So the deviation doesn't in reality doesn't represent the deviation from the mean. Okay, it is not the real physical deviation. If you want it, it's not the real physical deviation, right? So why aren't we just doing the real physical deviation, which is just taking the summation of xi minus mu over n? That's it. That would have been the real physical deviation.
Does this give the standard deviation at any value? Like instead of just from the mean?
That would not. We could just use mean here, right? Take the summation of xi minus u over n. Just forget the square and 1/2. Forget the 2 and 1/2. Okay. Why aren't we doing that?
Isn't this just like a convention for the normal distribution?
There's always a reason for a convention. It is definitely true that it is a convention, right? But why? Okay. Let me ask you this then. Let me try to guide you in the. You have to answer this question, right? Eventually, I'm not gonna give you the answer, but you have to answer. But I will try to guide you in a correct direction. Okay. Let's say, and for the benefit of the online people, I'm gonna do it in this. Okay. What did I do? Okay. Okay. Let's say we have this normal distribution and this is the mean. This is the mean. Okay. What is xi? This xi minus mean. Let's call this value of positive L. Right? What is this minus L? This xi. Let's call this xi2. This distance is negative L, right? So if you do it for every point on the two sides of the normal distribution, the summation of these will amount to what? All of these positive L's and negative L's.
They equal 0.
If it's a real normal distribution, it will be equal to 0. So essentially, you do all this as calculation, you eventually come for a value of 0 for your standard deviation, right? That doesn't happen, right? To remove that problem, you take this to the power 2 and then take the square root. But if you don't use the power 2 in the real world, because not everything is normally distributed, right? In the real world, that doesn't really happen. But since in our measurements, in our analysis, and to develop all of these statistical methods, we assume perfect normal distribution, we have to come up with a way that doesn't give us 0 value for a standard deviation. Does that make sense? Okay. So in the standard deviation formula, n is the population size, mu is the population mean, and the standard deviation gives us an indication of a bit of the distribution. Okay. But what's the difference between that standard deviation and the sample? That was the population standard deviation. What's the difference between that and the sample standard deviation? What's the difference in this calculation? The calculation are both of those calculated using the same formula, same equation, or no?
Will this one just be divided by sample size instead of the whole population?
No. That's what you would think that may happen, but that's not the case. It will be divided by sample size minus 1. Okay? And the reason for it is actually along the same lines as the previous one, because the statisticians who have studied this have concluded that dividing your summation of the scores of distances from the mean is going to give a better representation of the standard deviation of your sample. Does this make sense? That's what the study have shown. Their study have shown. So we just accept what the statisticians tell us. Okay. So, well, what is variance? As Lawson mentioned, variance is simply the square of the standard deviation for both cases, the population and the sample size. When we are going to use sigma squared for the population variance and s squared for the sample variance. Okay. So far we have talked about two different types of statistics. The first one talked about the measure of location, in which using those locations, using those measurements, we can calculate the mean, median, and mode. We talked about, we defined all of those things. We talked a good bit about all of those things, and you always have to keep in mind that statistics is any function of your data, any representation of your data. Then we talked about the variation of measurements of the spread of your data, with defining the variance, the standard deviation, the range. There are other types of measurement of the spread of data. One of them, other types of representation of that spread. One of them is the inner quartile range, which is the range essentially between the 25th percent of the data and the 75th percent of the data. That 75th percent range, right? And we also have another type of measurement of a spread, which is full width half max, which we are not going to discuss. So the next thing you want to talk about is the standard error. A standard error is essentially the standard deviation of the means. But what does it mean? Like, what does the standard deviation of the means mean? Because the standard deviation itself is a deviation from the mean, right? And we were under the impression that we have one mean, right? What does the standard deviation of the means mean? A lot of mean.
A standard deviation from the average of averages.
The average of averages, okay? So what those averages represent? Represent what?
Iterations of the experiment.
Huh?
The iterations of the experiment.
But that will be just one data set though. That will have only one mean.
Yeah, but you have multiple data that you have a mean of, right?
Let's say we go to the lab, we want to do the tensile test, the dog bone sample, right? Let's say you do that experiment 10 times. It will only give you one data set, right, and one mean. That's it. Where are the other means?
The other iterations.
Okay. So that I used to get confused here in the concept myself. So it is not a bad idea to discuss it a little bit more. So essentially, when we say the standard deviation of the means, we are talking about the measurements that has been done in different locations at different times, right? Let's say you do the experiment today, here, not today, and next Tuesday, here for yourself, you calculate a mean, a standard deviation, or whatever. We give you an idea of the spread, right? Someone else does the same calculation in Clemson, right? So that person will have another data set, right? Someone else does it in England, someone else does it in Asia, right? All of these different data sets can be combined and will give you different means, right? And standard error is essentially the standard deviation of the means of the means of all of those different data sets, right? Does it make sense? But you don't need to have those data sets to calculate the standard error. So the statisticians have actually come up with a formula that will give you an idea of what the standard error will look like, or what the standard deviation of the means will look like. You essentially have to divide your standard deviation by the square root of your sample size or population size. Very simple, right? Essentially, if this is making your analysis a little more accurate, it will make your range a little bit smaller without knowing the measurements they have done in Asia, for example. Right? Does this make sense? Okay. So, and how you represent your data is your data can be represented using your standard error, the confidence level of your measurement, which we will discuss a little bit, and then these two have to be the other way. So your estimate is going to be your mean plus minus the confidence interval multiplied by the standard error. Is there any one of you guys who knows what is the z-score, what is the t-score, or what are these confidence levels? So you are familiar with the confidence level then, right?
Mm-hmm.
So you use those z-tables, right?
Pardon me?
So you use those z-tables, right?
Or what? Those what? Z-tables, yeah. Exactly. So you guys are pretty familiar with the statistics part of it. That's good. Okay, are you still writing? Okay. So we have different confidence intervals, of course, but in general we can say the true value, and that is in quotation, right? Because we don't know the true value, right? Is essentially the measured mean value plus your z-score for the population multiplied by the measured standard error, right? So that's a standard error. That's not the deviation. That's the standard error. This is confidence level, and you already know that thing here. So essentially, what happens is when you increase your confidence level, it is increasing your confidence in your range, right? It is telling me, for example, let's say you represent something with 99% confidence level. It is telling me that you are 99% sure that the true value will fall in a specific range, right? Which is a very good estimate, 99%. But usually people accept a 95% confidence level. Okay. But we have to talk about this z-score a little bit more. Let's see. Let me ask you this. Let me ask you guys, because I have a feeling that you guys already are familiar with the z-score and the t-score. Tell me, what is the z-score?
So if you have a distribution and like 99% is all the way to the right end, and you look at the right tail things on the table and gives you the values for it.
No. What is the concept of it?
Concept? That's a good question. She would look at the tables right down.
It is always a good idea to know what's behind. At least have an idea of what's behind any phenomenon or any theory you use, right? So what is the concept of the z-score? No one? Okay, that's all right. We will talk about it a little bit, and then we will see the table and the t-score. And you guys are familiar with the t-score as well, right? What is the difference between the two t-score and z-score?
Different tables.
It could be like a two-sided tails and one-sided tail.
No. How would you know which one to use?
Is the T one dependent on time?
No.
Is it sample or population?
You are close. Yeah. For population, you always use the z-score. But you can use the z-score for sample as well. There is a limit on the sample size. If your sample size is small, you use a t-score which has a correction inside, right? But we'll get there. So let's talk about the Gaussian distributions. which are also called the normal distribution. They are named after the Carl Friedrich Gauss, which I'm pretty sure you know who Gauss is. At least you have heard his name millions of times in mechanical engineering, so you're pretty frustrated with the guy.
Is that the guy that did Gauss elimination?
Huh?
Gauss elimination, is that guy?
No. What's that?
Gauss elimination, we did that in numerical methods.
Gauss illumination.
Yeah.
Gaussian elimination.
Okay.
Yeah.
Yeah. It's the same guy. It's essentially the same.
This
guy.
guy ruined my life.
Yeah. So, who did you have your numerical methods with? Cyrus?
I had Cyrus.
No, I have somebody else. I think Mr. Wong did it.
Mr. Wong. Okay, but yeah. So you don't like Gauss. That's how I get it. Well, you'll end up appreciating him later on in your life when you get a little older. But essentially, it is the most common distribution, the normal distribution, in many engineering applications and any statistical analysis worldwide, right? And major-wide as well. Essentially, it is symmetric. This Gaussian distribution is symmetric around the central value. This red line here represents a normal distribution. The good part about it is a rule that I don't remember what it was called, but that's all right. Essentially, it means that if you can prove that for a set of data you have a normal distribution, which is usually what happens, right? And 68% of your data will definitely fall within one standard deviation from the mean, right? And 95% of your data will definitely fall within 2 standard deviation from the mean, okay? Roughly 2 standard deviation from the mean. And 99% of your data will definitely fall within close to 3 standard deviation from the mean, okay? So this is where the z-score comes into play, right? If you want to be 95% in your analysis, right? We already know that based on the normal distribution, the definitions of normal distribution, that it has to fall roughly around 2 standard deviation. That observation has to fall around 2 standard deviation from your mean, right? So if you have to represent that estimate, it has to be your mean plus minus 2 standard deviation, or in our case, z-score of 95% is 196, right? 196 of your standard error. Does this make sense? Okay. So the z-score is essentially the confidence level is telling you that how widespread is going to be your range of measurement, if you will. Okay? And what happens is, if you have a standard Gaussian distribution, what is a standard Gaussian distribution? A standard Gaussian distribution is something for which mean is 0, right? And the maximum value of u is 1. So you have essentially normalized your normal distribution, right? A standard. If you take the integral from that distribution from 0.196 to negative 196 to 1.96 to positive 1.96, you will get 95.95, which is 95%. Okay? Or if you integrate, as one of you mentioned about that one-tailed, the two-tailed condition, if you integrate from 0 to 1.96, you're essentially integrating on one tail of the normal distribution. Since normal distribution is symmetric, you can just multiply it by 2 and get the 0.95. This is going to be your the equation for your standard deviation, for your normal distribution in general. This is the equation that Gauss actually came up with. And essentially, if you're dealing with a standard normal distribution, your mu is going to be equation is going to be much simpler. Okay, moving on. I'm going to we actually talked about the Z scores a little bit. We talked about the Z statistic. This is going to be your distribution for the Z statistics, the standard normal distribution. As you can see, your mu is located at 0. The integral under the of the total thing is going to be 1. So the integral of this line, which is going to represent the area covered on the line, is going to be 1, representing 100% of your observations. Okay, and then you have the table for the Z statistic that you are pretty familiar with. I'm pretty sure you know how to work the table. Hopefully. Yes, you know how to use the Z table. Huh? Let's talk a little bit about a small sample size. If you are dealing with the sample sizes that have a smaller, some people say 30, but some people use 25. So in the next lab, we are going to use 25 as the cutoff value here. But here, you're not going to do any calculations for this, but we're going to use 30 for the cutoff value. So essentially, if you have smaller than 30 observations, the standard deviations and all of the statistical analysis will be very, very inaccurate, right? So to overcome that problem, this guy, which used the name student, then published this result with this method, came up with this new method of t-distribution, or a student t-distribution, right? The student t-distribution talks about the degrees of freedom. And degrees of freedom is essentially the sample size minus 1, right? So for different degrees of freedom, you're going to get a different t-score. If your degree of freedom is infinity, meaning that you're dealing with a population, your t-score is going to be the same as your z-score, right? And instead of using the z-score, you're going to use the t-score in the representation of your data, or in the calculation of your estimate or range. This is a t-score for the different degrees of freedom. And we are not going to talk about the probabilities, but I have it here. Very simple discussion about the probabilities and the proportions. But I will post this on Blackboard. If you're interested, you can just go over it. But it's just 3 slides. Okay, so let's talk about the experiment we are going to run. The fun stuff, right? Let's talk about the experiment itself a little bit, and then we'll move on to the theory behind it. So this week's experiment, and for the next, I think 4 or 5 weeks, we are going to focus on mechanical testing, right? We are going to have tensile test. We are going to have fatigue testing. Are you guys familiar with fatigue? The different failure modes, fatigue, right? And we are going to have a bending testing. We are going to have torsion testing. A lot of fun stuff. And but in general, what I want you to do is to do all of this analysis. Do them multiple times, to be able to do some statistical analysis on them, right? We're going to give, there are like 6 of you in the class, right? So I'm going to give you, each one of you 2 samples, or Surab is going to give you, each one of you 2 samples, and you're going to test them, like essentially you're going to have 12 data sets, right? For the 12 data sets, I want you to calculate the standard deviation for all of your measurements and include that in your modulus of elasticity discussions. You don't need to do any error propagation studies. We are going to do that next year. But I will actually include this in the lab instructions. If I didn't, please remind me to do this.
For a lab 3, is there a place to submit the lab report?
Lab 3. It should be on Blackboard, yeah.
No, I didn't see it. Did you see it? I don't see it there. I don't even see the lab 3 instructions on there.
There wasn't any lab 3 instruction?
I didn't see it. Did you guys see it?
There's only the lecture and the lecture notes.
I haven't looked yet.
Not even the recording for the class?
The recording is there and the PowerPoint's there, but there's no
Place to turn it in?
lab document
Okay, that's
or submissions.
okay. Please remind me whenever you don't see this before the lab, right?
Okay.
But the lab, to submit your lab report, I will open. It is due in a week, right? You
I
just
think it's due
on
the last
Tuesday. On
Tuesday.
Tuesday, yeah,
It's
on
coming up
Tuesday,
pretty
yeah, yeah.
quick.
Yeah, I will create a portal there today. Okay. If I didn't do it by tonight, please send me an email and remind me. Okay. Yeah, I'm teaching 3 courses. I'm doing a lot of stuff for accreditation of your program. That's why I was just talking about this with the other guys, with the lab 2 guys.
I think you're teaching design too right now, right?
I'm going to teach the design in the.
Because there were some people in proposal that were talking about.
Yeah. I'm so your capstone design. I'm going to teach the capstone design too. So you guys are going to have lab 1, lab 2 propulsion. I don't teach heat transfer anymore, but if you take heat transfer, you probably want to come talk to me as well if you have any questions.
No, I'm not gonna take that one.
Why not?
It's
Too
fine.
much math science. I'm good.
Okay. And then you will have your flight and orbital mechanics with me, as well as the design, capstone design. So 5 courses. If you end up taking the upper level aerodynamics, I'm teaching that one as well. So
The 500 level one.
Yeah.
No, you won't see me in any of those.
okay. So you want to get out of here as soon as possible, right? Get away from the math,
Get away from this place.
from the mathematics, or from this place in general.
Out of here.
Okay. I guess I don't know what to say. I'm happy for you. I hope you get out of here as soon as possible. But yeah, we can always talk about those things in detail if you like. If not, but right now let's focus on the lecture, and let's try to finish this in 15 minutes, okay? And okay, where was I?
Talking about the moduluses.
Yeah. So essentially, I will definitely upload. I will definitely upload the complete lab instructions by before end of this week, by tomorrow, and I will create a portal for your submissions, for your lab report submissions today. If I didn't, please remind me. Okay, so let's talk about the theory behind everything. We are talking about how materials respond to an external load. Think of a spring. That's the first example you always hear when you're dealing with how materials respond to a load, right? The Hooke's law, right? That's the idea, right? If you think of a spring, if you insert a load, or if you pull a spring, you are essentially exerting force on it, and you can calculate the elongation of that spring by multiplying. You can calculate the force that you are pulling on it by multiplying the elongation by the stiffness of the spring, right? That's pretty straightforward, and you guys have seen this a lot of things. Then we define a stress as a strain as your load divided by area, and we define strain as the elongation divided by the initial length. You have to keep in mind that the true stress is actually your load divided by the area, right? It divided by the area that is changing, not the initial area. Because if you pull on something your load is going, your area is going to, yeah, 1 hour and 40 minutes is too much for me. I forgot what I meant to say. Let me just read from it. It's fine. So dividing the load by the original initial cross section, A naught, is going to give you the engineering stress. But if you want to have the true stress, you have to divide it by your area that is going to change as you pull your whatever, the sample that you're analyzing. Okay? Any questions so far? We can have a stress strain curve. A stress is very, very familiar curve. I'm pretty sure you have seen this multiple times by now, right? The first part of it is the linear elastic region that goes from 0 to A, and after the linear elastic region, we are going to reach the yield stress, right? Which means that your material is essentially yielding to the load, and the deformations are not going to be elastic anymore. The deformation will definitely be plastic, meaning that whatever deformation you're going to see is not going to back to its original place, to its original shape. So you will eventually, even if you remove the load, you will have a deformed sample. Does this make sense? Right? We also have an ultimate stress, which is the maximum amount of stress your material can handle, after which your stress will decrease. Right? It doesn't really matter how much you increase the load, your stress will definitely decrease. And at some point your material will fail with fracture. This is what you are going to, essentially this is going to be a report for the upcoming lab. You have to give us a stress strain curve, and you also have to calculate the modulus of elasticity. Right? How do we calculate the modulus of elasticity? Is there any ideas?
If you had asked me last semester.
Huh?
They said if you had asked me last semester, I would have had that like that.
That's actually, I'm looking for a very simple answer. I'm not looking for
The
modulus of
curve
elasticity.
E or the other E?
It's this
It's
slope.
the curve E, right? So
Is the what?
Is the stress times the modulus of elasticity equals that modulus of that load or whatever it's called?
That's strain.
So this is a strain, this is your stress, right?
Uh-huh.
Yeah.
And
So is it just
they
this?
the two are related through modulus of elasticity, if you recall from your solids course, right? Okay. So my question is, how would you go about, let's say this is the only thing you have. You have all the information on this plot and that's it, right? How would you go about calculating the modulus of elasticity?
Divide them.
You divide it.
You just find the slope of the straight line in the elastic region.
Okay, that's actually that is the most important point, is the fact that we are talking about the modulus of elasticity. So we are only talking about the elastic region here, right? The elastic region is a linear region, right? So if I ask you to find the modulus of elasticity, you just forget about the other data you have. You take this data, you calculate the slope of this line, and you will have your modulus of
That's
elasticity.
the rise over line, just divide them.
Huh? Yeah. Just divide them. But if you divide the whole data set for yourself, it won't give you one number. It will give you a lot of numbers. It will give you a distribution, because the slope here is not linear anymore, right? The slope is changing, right? Does this make sense? And it is the modulus of elasticity, right? It shouldn't talk about the plastic parts. But we have different types of loading modes on our sample, whatever kind of sample is that. We have tensile mode, that essentially you're pulling a sample. We have a compressive load, which we are pushing the two sides of samples together. We have torsion, and we have shear. We are going to see experiments on the tensile load, compressive load, and the torsion load, but we are not going to see any shear experimentation. Okay, so let's talk about different materials, right? Let's talk about, let's say we have these two different materials, let's call them like 1, 2, 3, 4, right? 4 different materials. if the slope, and these three, the first three here, I have to go on the board. The first three here, do you see this point? It's a very small window. The first three here talks about the stiffness of your material. So essentially, if you have a higher slope, you have a stiffer material, right? If you have a lower slope, you have a more flexible material. What does it mean? It means that a flexible material is essentially has a lower modulus of elasticity. A flexible material has a lower modulus of elasticity, and a stiff material has a higher modulus of elasticity. Okay, but then the question is, what does it really mean, right? When we say, what does it mean when I say lower modulus of elasticity?
Then less plastic deformation.
Well, we are talking about modulus of elasticity. We are not talking about any sort of plastic deformation.
It's more flexible.
What does it mean?
Will yield sooner?
Yeah.
It doesn't necessarily yield sooner.
Oh,
no.
it takes a lower amount of stress to get same amount of strain.
It takes a lower amount of stress to get the same amount of strain, right? So essentially, let's say you want to have this much strain here. For a flexible material, you need to have this much stress. For a stiff material, you need to have this much stress, right? So it literally means that it is stiffer. You need more load to deform it, to change the shape. Okay. But what else do we have? We have two different materials. We have the ductility of the material. That's another component. That's another part that you have to make sure you keep in mind. We have ductile materials and we have brittle materials. What's the difference between those two? As you can see from this figures here, this is a ductile material. This is a representation of a ductile material. This is a representation of a brittle material, right? So what does it mean? What's the difference between the two?
One will fracture before the other does at a lower strain.
So exactly. So essentially, what you're saying is that one has a lower tolerance for plastic deformation, right? So essentially, it will the yield to the fracture stress. The difference between the two yield and fracture stress is going to be smaller in a brittle material. What is an example of a brittle material?
Peanut brittle.
What?
Peanut brittle.
Peanut is brittle.
Well, okay, so peanut brittle is like caramel and peanut butter, and whenever it cools, it gets really, really brittle. That's why it's called peanut brittle.
Okay. That's a very good example. We usually go for glass, but yeah, that's a very good example as well, as long as it is a brittle material. What's an example of a ductile material? Huh?
Taffy.
I'm just gonna throw this out there, steel.
It's two. Like a food is two?
No, steel.
It still has it still has wide range of different materials, right? The same is true for aluminum. You can have a very brittle steel, or you can have a very ductile steel, right? That's why people get PhDs on just a steel.
There's brittle steel.
If it's cool,
That's
it's probably can fracture a lot easier.
It's actually not brittle steel, but I meant there's brittle iron, right? What is brittle iron? Because it still is essentially iron, right? It's treated iron, right? What is a brittle iron?
Iron's brittle.
Raw iron.
You see, it is not just iron, right? You can treat iron. You can have different types of iron, right?
What is brittle iron?
When a blacksmith makes a sword but doesn't cure it correctly, it can be very
Yeah.
brittle after.
That is pretty brittle. Yeah, that can be pretty brittle. But we have a specific type of iron that is actually very famous for its brittlity, if you will. Does anyone have that in mind? I don't remember the English word, that's why I'm asking you.
Okay, how about aircraft steel? There you go.
Aircraft steel is ductile. No, steel is ductile in general. I'm not saying you're wrong, but there are different types of steel. There's different types of treatments you can do on steel. You can increase the brittlety, you can decrease it. You can increase the ductility. Right?
What is that brittle iron called?
I don't remember. Let me.
I didn't know it existed until now.
Brittle iron.
Yeah, who thought of that?
Just
Sounds
say
like
it
an
not in
oxymoron.
English. Maybe you'll be familiar.
It's paradoxical.
Why is it paradoxical?
When you think of iron, it's brittle iron. Those are two opposites. And when I think of iron, I think of something.
Oh, cast iron.
Ash
Ah.
iron. Okay.
Cast iron is brittle. It's a brittle material. You didn't know that?
I just said iron though. I didn't say cast iron. There's
Yeah, because I know a lot of gun manufacturers prefer forged iron over cast iron.
Yeah. So what is the difference between cast iron and iron?
How they're treated.
That's it. I said how you treat iron is going to change it. A cast iron is iron, right?
Mhm.
I can't believe I forgot the English word for cast iron. Not my native language. So, are we clear now? Yeah. Okay. So, yeah, I mean there are a lot of this is actually NASA experimental aircraft that has not materialized yet, but you can see the difference between the difference it makes to use different material in how wings are going to behave, right? And then you have a picture of the failure of the same thing, right? So the relationship between sigma and the stress and strain is actually defined by the Hooke's law, right? The Young's law. What did I say? Hooke's law. That's for the Young's law. Sorry. The Young's modulus of elasticity, and we can relate the two. That's what you need to do in the lab. Eventually, a high value indicates a stiff material, a low value indicates a flexible material, and we have a very important another important constant that comes into play because of the fact that it doesn't really matter what's the direction of your load, you will have a strain in both directions, right? Unless you have a clamp or something on your material, right? So we can have a transverse contraction here. That transverse contraction is related to your longitudinal displacement of your strain, okay, using the Poisson's ratio. So we can actually relate the transverse contraction to your Poisson's ratio, to your stress. We can have the same analysis for the shear stress. We can define the shear stress as shear force divided by your area. We can have the shear modulus G, which is analogous to your Young's modulus of elasticity. And we can have the shear strain, gamma, which can be calculated by tangent of your theta. We can apply load in different directions. Okay. We can have biaxial loading, right? But how can we analyze? How can we relate the stress and strain in a biaxial loading? What is the mechanism we can use?
plus stress y over 2.
So just take an average.
No, it
And it was times something else.
there was I wish I saw this notebook on me, but it's like sigma xx and then sigma yy and then sigma xy.
Okay, so we can actually using there are those, but you didn't give me the relationship, right? We can actually calculate the stress and the strain. We can relate the stress and the strain in each direction using the modulus of elasticity as well as the Poisson's ratio. So if you're applying the load in one direction, you will have a strain, you will have a transverse strain that is going to be related to your lateral strain in the same using the Poisson's ratio, and the lateral strain is directed to your stress using the modulus of elasticity, and then we can essentially only superimpose this, right? Using the superimposition method. So superimposition is very important in any type of analysis. So we simply means that we can add the two strains in the that are present because of the two different loads. You can just add them up. So your strain in the x direction is going to be the stress in the x direction divided by the modulus of elasticity minus the stress in the y direction multiplied by the Poisson's by nu over the modulus of elasticity, and so on and so forth. Any questions? I guess we can stop here. We can talk about the rest of it later on. The isotropic and anisotropic material. We can talk about it. We will have a lecture on composites. I can just add this slide to the composite lecture because it's very much related to composites, and we can stop here. Okay. Is there any questions?